This section covers reaction rates. Reaction rates are nothing but a speed, and you're probably familiar with something like miles per hour. Well, when we have a chemical reaction, we'll measure it in things like molarity per time. Notice here it says, you can measure the increase in concentration of product with time, or you can measure the decrease in reactant concentration with time. So those are two very, very simple measurements that you can do. What we want to do is illustrate it here. Let's say that the red are our reactants and the blue are our products. And in your textbook, they have this picture. If we look at the first one, notice it says 0 time. And at 0 time, there are 100 little red balls. They represented in the chart by 1.00. And as time goes on, we start to see some of those red balls turn into blue balls. So this is a beautiful way to look at it in terms of little balls that you can count, but often you will be given a table of data. So let's zero in on this 20 seconds. If I were to count them, I would be looking at this line in the chart. I would see 54 red balls. I would see 46 blue balls. Again, very simple to see. The third way data can be represented is in a graph, and let's just make a correlation. Here's our time of 20, and here we have our 0.54 and 0.46 corresponding to what's in the table, corresponding to what's in the container. Keep that in mind as we proceed through the chapter. It's very, very simple, the idea. So we can use those numbers to calculate what is called the average rate. And I'm going to emphasize the word average. We could measure the decrease of reactant with time, or we could measure the increase of product with time. And again, here is our picture with the little blue balls. The average rate has a definition. It is the change in moles, where we take the final minus the initial, divided by the change in time, where we take the final minus the initial. As long as you follow that protocol, nothing bad is going to happen, okay? So we can have B start to appear or A begin to disappear. Those are the equations. Here's some actual numbers. I went into the table and pulled the numbers out. If I want to look at the average rate of the decrease of A, what I would do is I would say, this is my final amount of A, this is my initial amount of A, and the time period is 10 minutes. So we have 10 as the final, we have 0 as the initial. It's kind of like taking the slope of a line. And we come up with a number minus 0.026 moles per minute, because we're counting those little balls as moles. What if instead we were looking at the average rate of B appearance? Well, we would do the same thing. We would count the number left of B, or the number that have formed in 10 minutes. Here's what we had initially, absolutely none. Here is our final time, and here is our initial time. If I do the math, what I come up with is the exact same magnitude. The average rate magnitudes will always be identical, and by convention, rates are always presented as positive numbers. So take some time to go through that. I typed it out ahead of time because it just takes too long to write down. Okay? Now, the average rate is always going to decrease with time. I don't know why your textbook authors threw in this example, but they did. It's primarily reactant going to product. If you look at the table, you see time is marching on. If you look at the amount of reactant, you will see that it is decreasing. And you can do the calculation that we just did on the slide before to come up with numerical values. All right, it's tedious, but it's here to show a point. What we see is that the rate starts out at a given number, but as time goes on, that number is going to become much smaller. Why does this happen? Well, in your textbook it says the concentration of reactant decreases. Let's go with that definition, okay? What else? There's also something called the instantaneous rate. Now, I'll talk more about this in Zoom lecture. I used this a lot when I was getting my PhD and also undergrad research. But instantaneous rate is the slope of the tangent. In the first section, you saw that we had the reactant amount decreasing. And so the slope this is also known up here as the initial rate. It's the instantaneous rate at time equals 0. Well, the hard part is, how do you measure that? As soon as your reaction starts, things start to happen. So what you do is you pick different times and you calculate, based on the tangent to that line, a slope. So when I did my undergrad research, I would set it up such that I would have the same time period using different additives. Your textbook shows what happens at 600 seconds. So essentially, they draw a line up from the x-axis, so we have a point here on the line, which they neglected to put in. Then they draw a line, and from that line, they take points. They take the x points and y points and come up with a slope. And that's essentially where the numbers come from that are shown. Once again, the number is going down, but it's used if you're doing a comparison. I was putting different additives into the artificial sweetener aspartame when I was a junior in college, and so that was how we measured things. We chose a time and we always analyzed it at that time. Spectrophotometric methods can also be used to measure reaction rates. I do not know which labs you're doing this term, but normally you run an experiment where you look at a color change over time. So let's say, why do we do these things? Well, we have some sort of source of light, we have some lenses, and what they're going to do is they're going to impinge a given wavelength on the sample. Once it hits the sample, it will be picked up by a detector, and since everything is computerized now, you'll just be reading something off some type of device. What you can do is look at how does the concentration and absorbance correspond to each other. This is called a calibration. And again, I do not know if you are doing this in lab this semester, so it's hard to go deeper. And the slope is what you would use to do your calculations for unknown solutions. I'm just going to say it is a method, so think about the A and the B values. This gives you values for molarity based on a color change. So what else is here? Well, stoichiometry comes back from chapter 3. Remember when we were back in 1210, we used our stoichiometric coefficients to balance our reaction. Well, now what we're going to do is use them in order to relate the rates. What will happen is each of these coefficients becomes the denominator in an equality. Oh, students really struggle with this. I am not even going to sugarcoat it. If I have a reactant like A or B, notice there is a negative sign because reactants are disappearing. If I have a product like C or D, notice there is a positive sign because products are appearing. What is it that you're going to have to do? Well, let's do two for instances, okay? Here is that old equation from chemistry 1210. Nitrogen plus hydrogen to form ammonia. We are told that the rate of nitrogen appearance is 2 molarity per second. There is a 1 in front of nitrogen, and there is a 3 in front of hydrogen. Well, 1 to 3 is the same as 2 to 6. 1 to 2 is the same as 2 to 4. All right, so pause this if you're listening and think about what we've just done. What if instead we had the number 5? Well, it's still a 1 to 3 to 2, so it would be a 5 to 15 to 10. That is how simple this is, but hopefully you can see it with a ratio. Now, those were beautiful whole numbers. What would it be if things aren't quite so pretty? Well, that's when we are going to use the rate relationship, because that way you can always come up with the proper number. Here we have a 2 to 1 to 1. So what I've done is I've taken that coefficient and put it at the bottom, because that's how the relationship is, and there's ones in front of the other ones. So if I started with 4 molarity per second, there we go. Minus 1/2 of 4 comes up to be a 2. So again, that is really how we are doing this, 2 to 1 to 1. So here we have a 4, and notice that after I do the math, all the numbers are equal, but we would have a 4 molar, 2A, 2 molar, 2A, 2 molar. Please ask questions. This always appears on the midterm. You'll see some, well, you saw in 1210 many practice questions. You'll see the same thing in 1220.